Today, we are pleased to welcome Professor Henry Medeiros from the University of Florida, in the United States. Professor Medeiros works in the field of artificial intelligence, computer vision, and robotics, with a strong interest in perception system for real application. So it is a pleasure to have him with us today to share his perspective on artificial and agricultural robotic perception. So, Henry, the floor is yours, so you can share your screen.
Thank you very much for the kind introduction. So today, let me get this out of the way. Apologize. Today, I would like to tell you a little bit about my own experience with robotic perception and artificial intelligence for robotic perception in agriculture. And I am sorry if I'm struggling a little because Zoom is hiding my view. So, okay, this is better. You can still see my slides, right? Okay.
Yes.
So, yeah. Well, there are just way too many potential applications of robotics in agriculture, of course, as you can certainly imagine. We just cannot talk about everything in this just a few minutes that we have together. But excuse me, I listed here just some of the applications where we have actually seen some real progress on, in some cases, some research or some even commercial applications of precision irrigation and yield estimation, harvesting, pruning, phenotyping, all those things. We've seen actual real progress in the last few years. And just to have an idea of what that means in practice, right, in the real world. So today we can, there are platforms out there that can do weed detection with an accuracy of 90%. Of course, that's a very broad statement, right? But in let's say, practical, real applicable conditions, and that can lead up to pesticide reductions of orders of 70%. And just to illustrate that we can see similar, potential in all those other applications. So I believe many of you here might be somewhat aware that the major manufacturers that are incorporating, AI methods into their systems. So in a sense, a semi-autonomous combine is a robot, right? And it has very similar needs in terms of the perception, right? The methods, the techniques, the systems, and the methods that we use to understand the environment, right? Such that the robot or the autonomous combine can do something about it. Of course, the big three, as we sometimes call them, they are heavily focused on row crops. That's their main market. But we are seeing a lot of improvement in other areas by smaller companies, right? So today, we see a lot of commercial platforms being used, offering surveys to monitor plant quality. Pesticide application, fertilizer application with drones is a reality today. So those are commercial services that are being offered. They're still at a smaller scale, but again, something that is growing very fast. And of course, we are starting to see some of those ground platforms that are coming largely from startups, of course, but we're starting to see some commercially available special purpose harvesters. We're starting to see different weeding technologies being deployed in the field, and again, they're starting to commercialize those. Also, ground sprayers that are the UAV-based spraying is great, but the problem is that you have to carry a tank around, right? So we could have some autonomous ground spraying. There's also a lot of market or great opportunities there. So what is enabling this new techniques to come out so quickly? Right? It's all, as I'm sure you imagine, part of the same revolution that we're seeing in all these other fields, right? As we saw, in semi-autonomous vehicles, for example, right? Those driver assistance systems. They have been driven by a lot of this this commodization, we could say, of the research tools that are relevant in this field. So we have, of course, more advanced platforms, right? So we have UAVs that with self-charging capabilities. The sensors have been evolving at a unprecedented pace. I'm showing here just a LiDAR because it's a nice illustration of a technology that not too long ago used to cost tens of thousands of dollars, and it was highly inaccessible, to being today almost, you can get toy LiDARs for, to build your own robot, and you get fairly good results out of it, using those community-supported, publicly available platforms, right? So one of them, the big things that is helping advance robotics is ROS and all the ecosystem. ROS is the robot operating system, which is supported by things like Nav2, which is a navigation framework, and Move-It2, which is a manipulation framework. So Move-It controls the robot arm. Nav2 controls its wheels, let's say, right? So you can easily get, and that's actually something that, with the done at the university with like the robotics team, you can get an off-the-shelf LiDAR for very little money and quickly configure it to run with ROS and have a fully capable self-localizing system that can map, where it is and drive around, and it's fairly easy to accomplish. But especially, I guess, maybe more important than, or as important as I apologize, let's get this out of the way. As important as the robotic technologies or the sensors and the robotics operating systems are the libraries that have allowed the dissemination of this deep learning tools and techniques. So those put together, the deep learning methods, well, I guess those all put together, they essentially are what are allowing us to advance robotic perception so quickly. And then, as I was saying, what do we mean by robotic perception? So basically, robotic perception is the ability of incorporating, information about the robot location, multiple sensors, and essentially create a model that allows the robot to understand the environment. That's essentially it, right? So it knows where it is and what's surrounding it. And again, the sensor, all the developments in those autonomous systems, they allow us to build those robots essentially. But what enables these perception models are those large scale multimodal deep learning models that we're seeing recently. And those models, they are largely driven by self-supervised learning capabilities as strategies. And I'll talk briefly about that, but it's important to emphasize those two aspects, because without self-supervision, we essentially have to teach the robot everything, right? Everywhere. Whenever you take it to a new field, to a new environment, the robot, to a new crop, you basically need to teach the robot what is going on. So self-supervision is driving the development of those, for example, those large language models that we see today, but it's essentially, especially critical for the kinds of applications that we are interested in. So as I should mention, with I was saying, we need, despite the fact that we are trying to create models that learn on their own, we need to be able to process a lot of data, right? So there's been what drove the progress of not just the large language models, but today we have those sort of multimodal large scale models. There are visual language models, and in robotics, we're starting to look a lot at visual language action models, right? Which are those models that essentially learn to solve language understanding tasks, but also vision tasks, and now how to take actions based on that. But all those models, they need a lot of data, right? So what allowed deep learning to advance was the fact that we had, those tremendously large data sets for different tasks, such as the famous MS COCO data set, which started about a million or so objects that people used for segmentation. There are lots of objects, for or larger scale data sets showing different kinds of scenes for detection and tracking. In agriculture, we don't have those just because collecting the data is challenging. And, we know a large part of the research in the domain is really going out there, getting the data and trying to understand, what it means. So whatever is publicly available today is very small. So what we need to do is we need, again, a way of getting models that ingest this kind of data. So they need to be large, so they have the capacity to learn what we need. But then, they have to be kind of briefly tweaked in using what's available out there. So here just briefly mentioning, the computational needs, right, of that kind of development. So we have at the University of Florida, we have this our high performance computing cluster we call Hypergator, and basically each team has an allocation, let's say, of resources there according to their needs. And just, this is, well, it varies, right? But this is more or less the average allocation that my team usually has. So we essentially use those 42 GPUs almost all the time, right? This is just a little plot showing that, at peak usage, we are easily using like 1,000, 1,500 GPU hours to train a model in a few days. So you need those, large models to understand those tasks. And then the potential here, so I guess what I'm saying is that all those developments that we're seeing in the field, they are made possible by those, those new advanced sensors, those very large models, and the availability of data, right? But that also, with that, because we are at this position where we can address those problems, there's a lot of room for growth, right? So we expect, we're just starting, right? So we expect the robotics market to, increase agricultural production, and we expect that, harvesting market to be, a billion-dollar market very soon. And drones, of course, they are already huge, and they're expected to get just bigger and bigger. So what are the challenges then? Right? So what do we need to do to design models for this system? Just so everything there is that I showed you so far, super specialized. And it's very specialized for a reason, right? So we have, agricultural problems are very different, right? So geographically, they're different. Operationally, right? So if you want to, a sprayer is very different from a harvester, right? So the tests are very different. The environments change. The temporal aspect is very, very critical, right? Because, as you can see here, we have a little example of, the difference in how apple trees change from, let's say, the winter time to when they're early in spring. So from the perspective of the robot, you're looking for a very different thing, even though it's semantically the same. So what happens then is that, as I said, we had this kind of, because we have limited data in this domain, we have no choice but start from these large models, right, that exist for general problems, sort of adjust them to our problem using our limited data. And then from that, we essentially need to provide labels that make sense for the application, right? So this is just an example of a tracking problem, which is necessary for robots in general. A robot has to be able to detect that, whatever it saw in one position corresponds to what it saw in a different position. So that is the tracking problem. And then there's even a more fundamental difficulty is that we have trouble coming up with evaluation metrics that are, that kind of work across different domains. all of those problems don't really exist in those large models that we see today for general purpose models. So what we can do then, what we try to do to address those is, we try to use different sensor modalities to learn from one another. We definitely try to, inform the models with what we know about, what's going on, like sort of, sometimes we think about it as you might have heard of like physics-informed models, but we can think like more general terms as like a process-informed model. And then of course we need metrics that work across, different domains. So here I'll just show you briefly a couple of examples, of robotic perception problems that, try to illustrate some of that. So in the plant detection problem, for example, right, all those tests, harvesting, spraying, yield estimation, most of the tests I mentioned before, we have an object detection problem, like a sub-problem. Here is object detection, right? So we need, let's say, this is for yield estimation, or bloom intensity estimation in this case, right? We can have, let's say, an object detection model that finds the flowers, or a segmentation model that gets the contours, but those are the closely related problems that we today almost treat them as equivalent, even though the data annotation needs can change quite a bit from one to another. So traditionally, right, to build a model like that, a model to address this problem, is we would build a large neural network, and then we would annotate it either with those labels or with bounding boxes, and then train the network to learn that. Problem is that then, if we train the network to find apple flowers, and then we need it to find peach flowers, then it just can't. So that's where this self-supervision comes into play, right? So if we have a model that we train to do a certain task, we can sort of use that model to create, this sort of course, we pre-train the model, right? And then we use that model to, make predictions that create sort of pseudo labels, and then it uses those predictions to learn from them, in a different scenario. Again, very briefly, I don't want to get into details, but just so that, you have a better perspective of what that means. Let's say in this specific model that we developed for segmentation of apple flowers, multiple species of apple flowers, we get this, we break those very high resolution images into small windows. Those go through what we call a panoptic segmentation model, which is just a model that can find different objects, distinguish them from the background. And so it gives labels to the objects, not only the instances, but also the semantics. Then that model, we generate a set of predictions, and by doing several augmentations, and we combine them. It's almost like a weighted average of those predictions. And those become our pseudo labels, which can then come back here, and be used to fine tune the model. So you can if you keep doing that for different species or flowers, you are able to kind of build this a self-supervised model that can work across, any, sufficiently similar problem. This is just briefly, the evaluation, comparing with a model that was at the time the state of the art in this domain. This model is trained on the different data sets. And then we have our model that's trained only on these data sets. It performs a little bit worse here, but it essentially maintains pretty much the same performance across different flower species without being trained on those. Extending that segmentation problem or the detection problem, it's we look at the object tracking, right? So as you must have imagined, right? Just seeing one picture for a robot is not enough, right? The robot will change its perspective, the robot will move. So it needs to be able to, know that, this lettuce plant corresponds to this one. That's a tracking problem. It's a lot harder because of it's a more complex problem because it incorporates the temporal aspect, but also the annotations are much more difficult because you essentially have to draw those lines. You have to make the connection. You have to tell the model to train the model. You have to say that this is lettuce one, or let's say this is lettuce one, and so is this, throughout all the frames that the robot will see, right? So it's what we do then is, of course, we are going towards full self-supervision, but an immediate step is to do like what we call weak supervision, where you provide labels. In this case, just the labels are for the detection. Of course, we could use the self-supervised model that does the detection, so we don't need these labels. But again, that's kind of the idea, is to build on the models. So here we use those labels, and then we do some unsupervised, like we try to estimate the motion of the robot based on those predictions, and then that motion is used to do the sort of the individual label association for us. So again, without getting too much detail here, we have in this case there's a sort of a one of those tracking models. That's where we call it Flora Tractor, which is a modification of an existing tracking model that is essentially a deep neural network that predicts bounding boxes and then does no maximal suppression and it estimates the trajectories. And then attached to that, we have this, what we call the spatial association module that uses this, it's called a local feature transformer that can essentially estimate the transformation from one image to the other. And then we use that to kind of move, to basically estimate where the bounding boxes move from, right, based on the robot motion, and do this association. So this is one of those kind of small benchmark data sets that we have in the domain today. This one is called Lattice MOT. It's a multiple object tracking data set. Again, it's relatively small, but it is, well, it illustrates well the problem, right, of keeping track of, let's say in this case, lettuce plants from a ground robot that has a camera facing down. And then we have those configurations where you can just go in a straight line, which is the easiest. There's, the robot can go and come back, which is a little more challenging because then you have to know that you're revisiting the area. And this is they'll call the out and in scenario, or ONI, which is the most challenging one, where the robot basically goes to the end of the field and then comes back through, another path, and then it needs to be able to tell that it's back there. So this is just to show our, the method that we called Flora Tractor Plus, and comparing with what was until recently the state of the art for this benchmark data set. This is a fairly sophisticated multiple object tracking method. And you can see that this approach of doing this motion prediction and association, it provides very substantial improvements in the essentially tracking accuracy and the F1 score based on the identities of the bounding boxes. And another nice thing about this methods is that, as I said, what you're trying to do is really scene understanding, right? So the goal of knowing that this is lettuce plant 9 is to essentially know where the robot is with respect to the patch. So from this, we can easily then reconstruct the trajectories of the 2D scene, that the robot observes. And this is just one of those other small data sets that are publicly available. I wanted to bring this so you would see that the challenge is still there, right? So you saw that in that previous data set, the results are nearly perfect. That's a very simple problem. But here, this is an Apple tracking data set, or segmentation and tracking, because here we keep track of the outlines. And you can see that our method, even though it is substantially, more accurate than what is the state of the art in this data set, there's still a lot of room for improvement, right? And that's the kind of thing we're working on. And the reason I think this method is particularly interesting is because, as I said, it's a weakly annotated method, right? So we trained it to detect the lettuce, we train it to segment apples, and then the tracking doesn't need additional labels. Right? The method kind of learns that on its own. And again, those problems, they might seem very specific, very simple, right? It's like, where do we go from there? So I guess first thing that we need to understand is that those are very fundamental methods that are being developed to be general, right? That's why the mindset is, trying to stay away from collecting additional labels. So we saw, for example, that same method that we use to detect flowers works fairly well to detect cranberries. The methods that, as I showed you, we're tracking the apples and lettuce, but we've been tracking all sorts of objects of interest, and it's essentially the same method. And same for the apologize for the segmentation and tracking, right? We developed this initially using lettuce. We applied it to the apples without much trouble. Now we're investigating, looking into a data set of cotton flowers, and again, this is just several others that are kind of works in progress. But not only that, it's like I said, this tracking, the detection is almost like the first initial problem. That's where everything starts, detection/segmentation. From that, we go to, it's the first stage of scene understanding. So from there, we go to tracking, and tracking becomes this sort of, now the robot knows not only what it sees now, it knows what it sees anytime. And then from there, we can easily go to like a full scene reconstruction, right? Because the robot understands enough about the world to know where it's been. And then, of course, those methods that I've been showing you, they are all 2D, just to keep things, how can I say, more accessible, right? So we can have a more informed discussion. But we've been essentially applying the very, very similar techniques to do that in 3D, right? And then when you do that in 3D, this is again the Apple sequence that I was talking about. Then we can do a 3D scene reconstruction, right? So this is again another, we have a simple model-based tracker that is based on the 2D version that I showed you. And again, without tracking annotations, we can do the 3D tracking and then reconstruct the scene. So we can see in blue the trajectory of the platform. In this case, it was a drone. And in red are the targets, which are the apples. And then, of course, as we go from, we can keep building on that, and then we go from the tracking to segmentation, right? And then we can not only get the bounding boxes. So again, this is model-based, so you can see little spheres projected in the scene. This kind of adds on that the segmentation and gets the accurate, outlines of the plants. And then again, we keep trying to do that without adding annotation needs, such that we go into this, the near future, this idea of full scene understanding. And this is just a little illustration of project that we're working on bamboo production automation, where we're building, this full 3D scene models and then extracting the semantic information, or the instances in this case are the bamboo combs, and we can segment and track them as we go. And I apologize, this should have been a little animation, but I don't know why it's not playing. And I guess just to summarize and wrap up so we can have a little bit of a conversation. Basically, what I wanted, the take-home message for you is that, and I apologize, I don't know what's happening to my picture here. So perception, these advances in perception models, right? So we are what's driving the growth in this new robotic platforms, right? So, or it's what is needed to support those platforms, right? So because we are seeing those new capabilities for, the lower cost sensing systems, we are being able to create more platforms that can do something useful. And there is now that we have seen some success in technology transfer, in several domains. We should expect that to keep evolve, right? It's almost like it's been validated, right? We now believe that there is the opportunity to create, let's say, commercial and deployable solutions in this domain, so that will only continue to drive this, this interest, because the need is there and it will always be. Thank you, and I'm glad to discuss the topic.